entire part. Correct?
Yes.
What did I say? Or shall I go to the syllabus and start from there?
Yes, sir.
Okay. Okay. Just hang on. Where is the syllabus? It was in the net. Syllabus is here. All right. Before you go to the syllabus, I have to share the screen with you. Are you able to see my screen?
Yes, sir.
Yes,
Yes.
sir.
Okay. So this is the syllabus for CFT. Before you go to the syllabus, I just give you a very small overview. Each line is 1 point. Okay. So overall process, we're giving you a very, very, bird's eye view of what you're going to do before we get into the next level of detail. The first one is we seek solutions not as continuous functions. Okay. Suppose analytically you have y is equal to x squared plus 2 as one equation. It's easy. Given any x, you can find y. But instead of that, we are giving it as a, for example, table form. For x is equal to 1, y is equal to 2. Y is equal to 3, y is equal to 1. X is equal to 4, y is equal to minus 5. X is equal to 4.5, y is equal to 2.5. X is equal to 5.672, y is equal to minus 2.7, and so on and so forth. Okay. We are getting numbers of the value of y only at some points in x. Understand?
Yes, sir.
Yeah. Now, if that is the aim, that is the aim of CFT. Okay, I'm giving you a very simple example. I'm giving you a very simple example. Similarly, you think of 2D. Okay, for x is equal to, x comma y on a plane, z is equal to something. Say velocity is something, pressure is something, temperature is something. These are usually the variables we worry about. U, V, W are three components of velocity. We bother about pressure, we bother about density. So generally 5 equations. If you have, there is the temperature will come in, temperature, or it is the energy equation will come, and density is there in incompressible flows. So we want the values of these variables in 2D at every x comma y, in 3D at every point x comma y comma z in a volume. We want the distribution of pressure, distribution of temperature, distribution of density. Suppose we say pressure distribution. Then we say what is the pressure at all these points in the domain. Okay. So now this can be constant with time. This can actually vary with time. In this case, we'll say, okay, at time t is equal to 0, time with t is equal to 0.1, what it is, the entire thing. T is equal to 0.2, how it varies with time. The whole points, the whole picture, you have to give it whatever time you need. In that case, you discretize the time domain also. So domain discretization is the first step. What we are doing is we are seeking solutions not as continuous functions, but rather we are seeking the output or values only at discrete points in the domain. Now this is visualized as grid generation. So you might have seen beautiful grids, we'll be showing some in the next few classes also. What does the grid mean? Wherever the grid lines intersect, hmm, we are seeking solutions only at those points. Instead of giving this as points or scatter plots, if you give it as a grid, you will know how they connect to each other also. Which point is connected to each other. That is necessary for getting the solution. So some kind of connectivity is also shown there. So grid generation is all about discretizing the domain. Where do you want the solutions to be? You can say, I want in a uniform rectangle, every, 1 centimeter of height and length and breadth, I want that. That's a uniform grid. More complicated one, less complicated, more is flat plate. In flat plate, at zero angle of attack or any angle of attack, say, I am telling the variation will be more near the flat plate because there's a boundary layer there. I'm solving Navier-Stokes equation. Now what happens? Near the plate, you'll have more variations. So to capture the variations, you want more points clustered near the plate. You know from physics that there will be more variations near a solid object because of viscosity. There will be boundary layer changes in the velocity. U component of velocity is there. So you cluster more points near the boundary. There won't be much variations far away from the plate. So you put less grid points there. So the grid will look a little bit different. I'm just verbally telling. I'll show you examples of all these in the coming classes. If it's an airfoil, in addition to clustering it near the body, we also want to cluster it near regions of high curvature. The leading edge, there is a lot of large curvature is there. That is where most of the changes are happening. So I want to put more point near the leading edge and less point near the middle and somewhat medium point in the trailing edge, where some more little bit of changes are expected. So you see, even before you design the grid, you need to know how the solution is going to look like. You anticipate the solution. You anticipate that there will be more variations in the properties in some areas. You put more points there. So the grid will be very packed there. Okay, you're interested more only in those points. You are less interested points that are far away. So put less points in those far away points. Unfortunately, you need to solve for the far away points also to get the value here. Okay, so you cannot do away with that, but put less points there. Even if you move a little bit here and there, the property is not going to change so much far away. So grid generation is discretizing the domain. Any doubts? Any doubts? Yuvan is there, no? Where is Yuvan?
Yes, sir.
Have you combed your hair today?
Yes, sir.
Ah, so can we have a?
Yes, sir. Yes, sir. So should I open now, sir?
Yeah, sure. I'll share again. All of us need a break. Okay. Let's see some Yuvan Krishna here.
Yes, sir. Yes, sir. So can you see me, sir?
Oh yes, yes. Only the top part. Only now you are showing only your hair. We believe that you are combed your hair. Yeah. But probably you can. Ah, yeah. Oh, yeah, yeah, yeah. Oh, fantastic. I remember you very well, but I
Okay,
just don't remember your name. Good, good. Okay. Thank you. Thank you.
sir.
Thank you. Yeah. So now let's go back. Whenever I don't remember, connect the name to the face, I will go to this. Oh, I'm sharing something else. I'm not sharing, right? I have to reshare again, right?
You're sharing it, sir, already.
Already sharing. Okay.
Yes.
Okay. If possible, mute your end when you're not talking. When you want to talk, you can unmute and shoot your question. No issues. Because of the disturbances in the background. Hmm. So yeah, next one is you're actually, when you go for analytical solutions, I told you those coupled partial differential equations are there. One for continuity, which is mass. Okay, mass is conserved. Another way to tell it in fluid dynamic way is continuity equation. We call the same equation as continuity equation. That's a partial differential equation. Then in momentum equation, there are three of them: x momentum, y momentum, z momentum. If you consider 3D flow, or only x and y momentums if you consider 2D flow, or only x momentum if you consider 1D flow. Okay. Have you done 1D flow analytical somewhere before? You remember? Even Krishna?
Yes, sir.
One-dimensional flow. Have you done somewhere in your BTech earlier? Anything related to one-dimensional flow?
So I forgot, sir.
Quasi one-dimensional flow?
So I think I've heard it in the second year, I think, sir.
But what is it related to? Quasi one-dimensional flow is used in
Uh,
nozzle, no? Nozzle relation.
yes, sir.
When,
Yes, sir.
when area varies, how does Mach number vary? How does all the properties vary? Mach number area relation. That is quasi one-dimensional flow. Quasi. Why is it quasi? There's something in the world quasi. Okay, find out what it is about.
Okay, sir.
Everybody is going to ask you this question. What is your project? Final year project. Even Krishna, what is the final year project? You have muted yourself, so
Sir, yes, hypersonic inlet, sir.
fantastic. I am going to ask you this question in your review. What do you
Okay,
mean by quasi one-dimensional flow? Quasi static. Hmm?
okay, sir.
So it is relevant to your project. Get it. You know, get the doubt straight.
Yes, sir.
Yeah. Okay. Good. So now you are working with Krishnan sir or
Shri Krishnan, sir.
Sri Krishnan sir. Okay. Good. Krishna meets Krishna. Good. Now what is the next one? Yeah. This is a different syllabus. Ah. So in these points, we want all the numbers. Actually, we have only the PDEs. Okay, 3 plus 1, 4, mass and momentum. If it is compressible flow, you have one more energy equation because you get temperature also into the picture. So you may have one more like P is equal to rho R T or something like that maybe. If temperature also enters the play. So in the worst case, in the simplest case, most general simplest case, I don't know how else to put it. Or the simplest one, you can say it is one dimensional. U varies with X. That's all. Okay. Then it's incompressible, so density does not vary. Even then, you have two PDEs. They are coupled together. One mass and one momentum. The most complicated case, 3D case, you have one continuity, three momentum, one energy, five equations, and plus one this one. on temperature, that is constitutive relation between temperature and something you need. Okay, if it's real gas, if it's ideal gas, P is equal to rho RT will do. Otherwise, some other relations will be there. So these are all continuous functions. PDEs are continuous. They are described everywhere in your flow field. Now we have to discretize these also, because if your domain is discretized, you cannot solve PDEs in them. You can solve only algebraic equations. Now the PDEs will have terms like, dou u by dou x, etc. Dou v by dou t, and so on and so forth. Okay. Now I have to convert this to some other way. Okay. Have you done this in FEM? I don't know. For example, dou u by dou x, I can say u2 minus u1 by x2 minus x1. I simplify like this. It becomes algebraic equation. Have you done something like this in your FEM?
No, sir.
No. So this is, you are representing the derivative itself by something, some linear items like u and v at some points. Okay, I can call it as u at I plus 1 by u minus u at I. I is any point in the x-axis by x at I plus 1 minus x at I. Now I can apply it to any point I in the x-axis, correct? So such kind of thing, what you do, you substitute for dou u by dou x, only this one. Then if you have dou squared u by dou x squared, something like this you do. Okay. So finally it becomes algebraic equation at a point I. It will be at point I. You substitute all these such variables. Okay. Dou u by dou y. For example, when you have the continuity, you have u dou u by dou x plus, what is that equation continuity? Dou u by dou x plus dou v by dou y plus dou z, dou w by dou z is 0. Am I right? Is it
Yes,
continuity?
yes, very
Yeah. So there dou u by dou x, you substitute this. You substitute ui. So that ui into this, you will get some equation, correct? But algebraic equations. Okay. So at one point I, you substitute dou u by dou x by this. Same way, you substitute that dou u by dou x, dou v by dou y by similar expression, dou w by dou z by similar expression at one point. Okay. Now, if you are telling I is 1, then you need to know the value at I is equal to 2. Now, that is connected to I is equal to 3 and so on and so forth. So, we form all the equations at all i's. How many variables will have? Dou e by dou x at, suppose I is equal to 10 points. For that, you know how to the u at all the 10 points. You don't know it initially, so you actually start with a guess. And you keep on iterating until it satisfies that algebraic equation. Okay. In this process, what we do is, I'm going to a little bit in depth now. I don't know why I'm doing that, but I'll come out of it now. All I want to say is, what was earlier a PDE is now actually an algebraic equation on the discretized domain when you want to express this or simplify this PDE. Such equations are known as FDEs. FDEs are known as finite difference equations. Okay. So instead of solving the continuous PDEs in the continuous domain, we are solving an approximate representation of the PDEs, which is known as FDEs, finite difference equation. We are actually solving only this FDEs in CFD. We are not solving the PDE directly. This FDE itself, there will be error when you do like this. We acknowledge that there is an error. This FDEs again are solved not continuously, but they are solved in the discretized domain. So there is a discretization error. Okay? When you want to, approximate a circle by a series of straight lines, you commit an error, right? Right or wrong? Abhishek. Abhishek is here?
Yes, sir.
Yeah. So suppose I take only 3 points on the circle and say this is my circle. Will you agree?
No, sir.
No. If I take, say, okay, 5 points,
Better than 3.
if I take 50 points,
Then it will be better, sir. It will be better.
it will be better. Will it be accurate? It won't be accurate, but you get a better approximation.
Yes, sir.
Correct?
Yes, sir.
Same way, if you increase the number of points here, you will get a better approximation of the PDEs or the space domain.
Yes, sir.
Idea is to get more and more points so that you get more and more accurate as far as mathematics is concerned. I mean, by mathematics, I mean the PDEs to FTEs are concerned. If I choose a small,
Method.
again,
Small approximate method.
yes, approximate. It is an approximate method.
Yes.
So this delta x, if it is small, the discretization error will be less. Do you agree with me?
Yes, sir.
If delta t is less, then discretization error will be less. Those are the points and times at which I choose to have the solution. Okay. So this is understood means there's a big leap of understanding, big leap of learning in that. Okay. The next step, thanks Abhishek, you can mute now. Now you solve this FDEs in the discretized domain and you get, suppose, given that you are not solving completely, it's an iterative process most of the time. You start with some known assumption, some assumption you start. Then you refine the assumption, keep on refining it every cycle. That cycle is known as iteration. Okay, we call it as one cycle, we call it one iteration. So after every iteration, the whole set of, say, U, V, or W assumed to be correct will change a little bit. Initially, because it is far away from truth, it will change a large amount. When you get refined, at some point the changes will be pretty small. Now, how do you define how small is acceptable for you? I say, for example, I may say with Abhishek in the earlier example that the if there are 5 points, it is good enough for me. No, I want 50 points. No, even that is not good enough for my purpose. I want 500 points, 5,000 points, 50,000 points, 5 lakh, 5 million, 5 billion. Where is the limit? Where do you draw the limit? Okay, that is depending on the problem and the person for what purpose you are doing the problem. Okay, so the changes you measure somehow how much has changed everywhere. If the changes become very less, you stop the calculation. Otherwise, you'll keep on going for infinity with very little fruit. Okay. So at some point, you may have to stop the calculation. When do you stop? When you say that the error is now below the limit which I specify. How do you measure that is a different issue. Now, this process of reducing the error with each iteration is known as convergence. So when you say that a solution is converged, that means that after one more iteration, you won't get any different the solution which is much different from the earlier one. We are not telling whether solution is correct or wrong. We are only telling the change in solution is now stopped. Then you say solution is converged. Is it clear, Sandita? Who gave the last presentation today?
Myself.
Who is that?
Giridhar.
Giridhar. You understand what is convergence?
Yes.
Okay, good. Right. Who are your teammates for that? Giridhar?
Yes, sir. Rashmita,
Yes.
Adarsh, Swaroop,
Ah.
so on.
Okay. So now, so get solutions at all points, iterate. Finally, you say that you are getting the solutions at all the points. Okay. Then you say that, okay, this is my solution. Then you want to see numbers is very difficult to visualize, especially in 2D and 3D. Let's say 2D, I give you 2D numbers. How difficult will it for you to, find out what format I have given in? Then, these numbers are varying, pressure is varying this way. It will be very difficult. So we have to render the data using the computer and visualize it. Then you know the trend. Oh, okay. So my pressure is varying more near the nose as expected. Varying less near the trailing edge or where there is a flat surface as expected. So it gives me more confidence into whatever calculations I have done. Probably it is very patchy, so the number of grid points may not be enough. Let me put more number of grid points and try. So to get this, you need to visualize it. Okay. So the next step is rendering the data and visualization. This comes in a process called post processing. This is post processing. You can also gain insight about the data. Out of some value, what is the maximum value of that variable, maximum pressure that is happening, minimum pressure, what is happening. Okay, those things also we can extract from this at this stage, in post-processing stage. Then you get the result, you visualize them, look at them, then you get some insight. Okay, so this is what the result says. If you are in the early stages, you need to know whether it is working correctly or not. So you may have to compare with experimental results. As I told you, the results you get only say that the solutions are not changing if it is converged. But whether that solution is the correct solution, because you have discretized, there is an error there. Okay. Then when you carry on the computation, every time you represent a number, you chop off. Correct? Your computer has only 64 bits. But actually your number may be a irrational number which goes to infinity. So chopping it off and do the calculations. Won't there be an error because of that? Yes, there will be error. So what is the combined error? Will my solution still accurate? I am getting converged solution, but is it the right solution? So to get the doubt cleared, we have to validate it first. After validation with experimental results or other computation results, you feel that it's matching closely in many of the cases for which you are interested in. You go ahead in the unknown cases and predict, okay, this is the result I am getting. Or if there is no computational results earlier, you say that, it looks like this trend is predicted, so better watch out. If you can draw some inference from there, you do more calculations and verify whether what you are doing is exact, correct. So it's not a joke. You need to do a lot of stuff when you do CFT. Okay. So I just wanted to get it off my chest before you go to the syllabus. Okay, now to the syllabus. Unit 1 will be Introduction to Numerical Methods. So it will be going more into the properties of numerical solution, just what you were telling. When you want to do this numerical solution, that is discrete and everything, you get errors. What type of errors are there? You've seen already. Consistency. Whether if you change the number of points, that is one more thing. Suppose I increase the number of points, solution changes. Then you say that, oh God. So if I increase more number of points, solution may change more. But after some point of increase, we find that no, the solution is actually okay. It doesn't change much by increasing number of points. So any more number of increase in number of points is only wasting time. So then consistency. Okay, if you do it many times, does it give the same result? Sometimes you assume random numbers. If you run the second time, will you get the same result? That's consistency. And in your computer, it is running giving this result. If I take the same thing to another computer, is it giving the same result? Because the precision of that is different. Every time is multiply, it will chop off different number of digits. It has a different operating system with just multiplication in a different manner. All this is consistency. Okay. So when you do a solution, you have to specify what system you are working on, what is the nature of that system, everything. Then accuracy, like you compare with known results to prove that it is accurate. Although you get a converged solution. Stability. If the solution does not converge, then it is unstable. If it converges, it is stable. How do you predict whether it will converge or not, even before you start the solution? This greatly depends on the kind of FDE you choose. The dou u by dou x, when I told u2 minus u1 by u x2 minus x1 is just one way of doing it. If I want the dou u by dou x at point 2, I can also have u3 minus u1 by x3 minus x1. There is one more way of describing it. Now, which of these ways better for the solution? We don't know. So that will affect the stability. Even before you start to employ the FTE, you can have an idea whether the solution will converge or not. If it is not stable, it's not going to converge. Okay. If it is stable, it may converge. Now, this convergence also, you don't want to wait till the end of your life to get a solution. Okay. So you want to, make it as quick as possible. So there are convergence acceleration techniques. Then conservation is used. They have to satisfy those PDEs finally. So you finally, after getting the answer, you check whether they are actually satisfying it or not. If they are not satisfying, then what is the percentage by which they deviate? Okay, or how much? What is the error? Not necessarily percentage. What is the quantity by which they deviate? So it has to conserve mass. It has to conserve momentum. It has to not conserve. It has to obey the momentum principle. It has to conserve energy also. So these basic properties will be unit 1. Then review of governing equations of fluid dynamics. That will be the equations which we are talking about. Continuity, momentum, and energy. Then review of classification of PDEs. Now these PDEs themselves, because the CFD is just an application of numerical methods. Numerical methods are basically discretizing PDEs. Now you should know the nature of these PDEs, what you are going to solve. Then the solution will also exhibit the same nature. You will know when you get a solution, hey, this seems to be physically correct. I don't have experimental results, but physically, my method seems to work. So you should know the nature of PDE for that. Basically, we have 3 types of PDEs. elliptic PDEs, parabolic PDEs, and hyperbolic PDEs. Okay. And these coupled systems, what type of PDE do they belong to? To make matters worse, they can belong to any of these PDEs. To make matters even worse, sometimes you can have a mixed. In some areas of your solution, it is parabolic. In some regions, it is hyperbolic. In some regions, it's elliptic. So you need to know the nature of your PDE. How to do it for PDEs in general, we'll see first. Very simple thing. Then for our own purpose, we'll see later. Then the physical implications for compressible flows. This is more important for compressible flows, where you can have a mixture of all these things. And viscous flows also. Then we will go to that finite difference method. That is how you are actually discretizing your PDEs. The PDEs you are converted to algebraic equations. No? So what are the different ways of doing it? How do you do it? Temporal is time, spatial is space. Okay. How do you discretize these things? Then as a whole, I have discretized only dou E by dou X. Suppose equation have more terms. How do you individually put them all together in an equation, get the equation? And how do you solve them? While solving them, if you go bit by bit, like you solve the first ones, which will affect the second column, then third column. That approach explicit. It is easier per time step, but then it will take a lot of number of time steps to get a converged solution if you use explicit approach. Then implicit formulation, which is you take all the variables together and solve them as a whole one. Okay. In this, you will get the solution within very few iterations, but per iteration it is going to take a lot of time because a lot of people are involved. I mean, a lot of points are involved. Then we'll see explicit formulation, which is McCormack scheme, one way of formulating the FTE and how to get the solution. We'll get this McCormack scheme. Then we'll see by means of a trick how we can extend to. This is basically for inviscid flow. Okay, inviscid compressible flow. You can use McCormack scheme. Now, if you want to use it for viscous flows, how do you do it? How do you trick? How do you play some low down trick to extend it to viscous flows? Then, if you have a compressible flows, what should you do for capturing a shock? Unfortunately, with regards to boundary layer, we know where the grid should be clustered and everything. In case of shocks, you don't know where the shocks are before they are formed. Only after they form, there's a shock. So this says that you need some more refined method to capture a shock. So we'll go to one more method called Lax-Wendorf method, which is a different formulation of the same McCormack scheme, but it's called a two-step method. Easier to apply this than that. Implementation. So this will introduce you, give a flare of what is finite difference method. How do you form a finite difference equation and solve it? Okay, I'll stop here. We'll go to unit 3 next class. Is it clear? Whom should I ask now? Niveda, is it clear?
Yes, sir.
Is it boring?
No, sir.
Okay, good. Krishna, is it boring or okay?
No, sir, it's not.
Okay, good. If you find it boring, just tell me. We'll do something. Okay. Then if we take attendance, we can stop the recording. No, it's not recorded. Huh?
It was recorded.
Recorded. Okay. You can stop the recording.